So we have a set of vectors like v1, v2, etc., vp, right? Each of these are a vector. We say these vectors are linearly independent if and only if this equation that you see here has only trivial solution, has only zero solution. It doesn't have any non-trivial solution. So v1 to vp are vectors, x1 to xp are scalars. So this equation is the vector form of a system of linear equations, right? x1 to xp are unknown. So this system of linear equations, if the system of linear equations has only trivial solution, then we say v1, v2, etc., vp are linearly independent, مستقل خطی. If this system of linear equations has non-trivial solutions as well, then we say that vectors v1, v2 to vp are dependent or وابسته, right? So this system is a homogeneous, متجانس or همگن system. Is if this متناجس system has only trivial solution, then v1 to vp are independent or مستقل. If this متجانس system has both trivial and non-trivial solutions, then v1 to vp will be dependent or وابسته.
Sorry, doctor, our classmates, they want to join your class. Please prove. Can you prove them?
Okay. So if v1 to vp are linearly dependent, any non-trivial solution which is weights of v1 to vp is called a dependence relation. A dependence relation, let me admit, a dependence relation is a non-trivial solution of this system of linear equations. Let's see an example. For example, let v1 be 1, 2, 3, and v2 be 4, 5, 6, and v3 be 2, 1, 0. So, what do you think about these three vectors? Are they dependent or independent? v1, v2, and vp. Are they dependent or independent?
No, it's not.
It is dependent, Doctor.
Dependent.
Why are they dependent?
Only at this value.
So we have these three vectors and we want to determine if they are dependent or independent. So you answer.
Solution first, right?
Sorry?
We have to find the solution first, then we can know it's independent or not.
Exactly, and find it. So pick a paper and a pen and find solutions of x1 v1 plus x2 v2 plus x3 vt equals 0. And let me know if these three vectors are dependent or independent. The trivial solution.
Yes.
Okay. Let's see the answer. So this is the matrix, the augmented matrix of system of linear equations x1 v1 plus x2 v2 plus x3
It's
v2.
independent, Doctor.
Sorry?
It's independent.
It's independent. Okay, let's solve this.
Dependent. Sorry, dependent.
Dependent.
Because we have the free variable.
Okay. Okay. Yeah. So this is v1. This is v2, and this is v3, and this is 0, the right side values. We try to convert this into echelon form, and this is echelon form, right? So do you see any free variable in this form?
Yes, x3, it's free.
Yes, your friend is right. X3 is free. It doesn't have any pivot position. So this means the system of linear equations has many solutions. So this means it has trivial and non-trivial solutions. So this means these three vectors are dependent. They are dependent, right? Okay.
Right, Doctor.
Now find the dependence relations between V1, V2, and V3. Now we want to please turn off your microphone when you don't want to speak.
Doctor, can you repeat that, please?
Please turn off your microphone when you don't speak. Okay. Okay, because of the reflection of voice. Okay, so we converted this system of linear equations into echelon form, and in this echelon form we have a free variable. X3 is a free variable because in the third column we have no pivot position. So this means this system of linear equations has many solutions, including both trivial and non-trivial. So now we want to find dependence relations. Until now we understood that these three vectors are dependent, right? So now we want to find dependence relations. For this we continue and convert the matrix into reduced echelon form like this. So x3 is x1 and x2 are basic variables, and x3 is a free variable. The first row gives this one, the second row gives this one, and the third row of the matrix gives this one. You already know how to find these rows, right? So based on the first row, we have x1 equals 2 times of x3, and x2 equals minus x3, and x3 is free. For example, so these three equations determine the dependence relations. So, for example, by setting x3 to 5, like this, x1 will be 10 because x1 is 2 times of x3, and x2 will be minus 5 because x2 is minus of x3. So in this way we find a dependence relation. We have many dependence relations. One of them is this one, x1, 10, x2, minus 5, and x3, 5. x2 minus 5 and x3, 5, right? 10 minus 5, 5. This is a dependence relation. If two vectors are dependent, how many dependence relations can we find between them?
Many.
Yes, many, infinitely many.
Infinitely.
Yes, infinitely many, because in this case we will have a free variable and we will have infinitely many solutions for our system of linear equations. As a result, we will have infinitely many dependence relations. So one of these dependence relations is something like this. 10 times of V1 minus 5 times of V2 plus 5 times of V3 gives 0. So you see that coefficients of V1, V2, and V3 are not 0. So this is a non-trivial solution. So is it clear for you until now?
Yes, doctor.
Okay. Now consider a matrix like A and assume that it has columns like A1, A2, and AN, right? We have a matrix like A whose columns are A1, A2, and AN. So we can consider each column as a vector, right? So we can extend our discussion about the dependence and independence of vectors to the dependence and independence of columns of a matrix, right? Because each column is a vector, right? So consider columns of A, and so we can have this equation x1 a1 plus x2 a2 etc. xn an equals 0 to check if columns of the matrix are dependent or not. This is something like that, right? This system equals to this system. This one is vector form and this one is matrix form, right? So we can use this notation x equals 0 and check if this system, this equation has non-trivial solutions or not, to see if columns of A are dependent or not, right? Very simple. You can consider each column as a vector, and then you can talk about dependence and independence of the columns of the matrix, right? Okay, now let's talk about some special cases. If we have just one single vector, in our set of vectors, V1 to Vp, we have just one vector, V1, P equals 1. So in this case, we have just one vector. In this case, is it dependent or independent? A set consisting of only one vector. Is this dependent or independent?
It's a one vector. It's independent, doctor.
So your friend says independent. What about the others? Do you have any opinion?
You meant, doctor, you meant if we have just basic solutions?
So we have a vector like V. If this
Yes.
set of vectors is dependent or independent? offset consists of one vector.
Also, maybe it's dependent, but maybe just one solution.
Okay, what about the others?
It's independent, Doctor.
Okay, thank you. I want
Doctor,
to say,
Doctor,
Yes.
each linear dependent on the among the column.
we have just one column. We have just one column. We have just one vector. So this
If one column, it's just it's independent, Doctor.
is independent.
Yes, because we don't have another x. It's need to find its value or variable from another one.
Okay. Okay, thank you. I want to say it depends on the value of that single vector. Let's call that vector v. We have a single vector called v. So if v is not zero, v is non-zero, x1, v1 equals 0. v1 is not 0. So the only solution for this equation is x1 equals 0, right? It only has a trivial solution. In this case, v1 is
Doctor, please, can you approve some student, please?
we should try to come on time. Okay. Because I'm seeing some other page. I don't see the page of the Google Meet. So I don't get noticed. Anyway, so if v1 is non-zero, then x1 v1 equals 0 has only trivial solution, which is x1 0. In this case, v1 is independent. So if v1 is non-zero, it is independent. It is independent from itself. But what about if v1 is 0?
Dependent.
It's dependent.
Dependent.
You mean the vector is zero?
Vector 0 is dependent.
Dependent.
Yes, we have only one vector, and that vector is 0.
Yeah, it will be dependent.
It's dependent because
It's dependent,
we
Doctor.
have a more than one solution.
Exactly. When we have only one solution, when we have only one vector and coefficient, and it is 0, whose coefficient can be anything, right? Whose coefficient x1 can be anything, 0 and non-zero. In this case, v1 is dependent because we have non-trivial solutions as well. So when we have one single set, if that's one single vector, if we have one single vector, if that vector is 0, then it is dependent. If that vector is non-zero, then it is independent, right?
Independent. Okay.
Okay. So now consider the case of two vectors. We have two vectors, v1 and v2. If one of them is 0, what would happen? For example, v1 is 0, v2 can be 0 or non-zero. What would happen? Are they dependent or not?
If it's 0, Doctor, it's dependent.
Dependent, at least 1 0. One vector is 0.
Exactly. So if we have two vectors, v1 and v2, and at least one of them is 0, then in this case, they are dependent. In general, any set of vectors which has 1 0 element, 1 0 vector, it is dependent. In general, you can say any set of vectors whose at least one of elements is 0, then it is dependent, right? Do you agree?
Sorry, Doctor, can you repeat?
So if we have, in general, if we have any set of vectors like v1 to vp, and one of the vectors in this set is 0, then this set is dependent.
Yes, Doctor.
Because the coefficient of 0 vector can be non-zero, and the system will find non-trivial solutions, right?
Right.
Okay, so let's get back to the case of two vectors, v1 and v2, and none of them is trivial. None of them is 0. v1 is non-zero and v2 is non-zero. So are they dependent or not? And when they are dependent, then they are independent.
Excuse me, doctor. Could we get example to explain it more?
So we have two vectors like vx1, v1 plus x2, v2 equals 0, right? And v1 is not 0, v2 is not 0. Are they dependent or independent? This is my question. Are they dependent or independent?
Doctor, if we have two vectors, that's independent. If at least one of the vector multiple of the other.
So from this, if at least one of them is non-zero, I mean, it should have at least one non-zero solution, right? Non-trivial solution. So at least one of to be dependent, right? In order to be dependent, at least one of x1 or x2 should be non-zero, right?
Right, Doctor.
Let's x1 is non-zero.
Here we have trivial solution, right?
We want to see what happens. We want to see what happens when v1 and v2 are dependent, right? So let's assume that v1 and v2 are dependent, and let's see what happens in this case, right? So v1 and v2 are dependent. So this system has non-trivial solutions. So at least one of x1 and x2 are non-zero, right? At least one of x1 or x2 has non-zero value, right? Because it has non-trivial solution. Let x1 be non-zero. So x1 is non-zero. We divide both sides by x1. We can do it because x1 is non-zero. So we will have v1 equals minus x2 over x1 v2. So this appears. What does this mean? What does this mean? This means
This
if
means that
v1,
okay.
sorry, continue.
This means that the multiple of vector is the vector is a multiple of the another vector.
Exactly. This means when we have two vectors and none of them is 0, then they are dependent. One of them is a multiplication of the other. If they are independent, none of them is a multiplication of the other. So you should keep this in your mind. When we have two vectors, if they are dependent, one of them is a multiplication of the other. If they are independent, none of them is neither of them is a multiplication of the other, right? So if they are dependent, one of them is a multiplication of the other. If they are independent, neither V1 nor V2 is a multiplication of the other, right? Is it clear?
Doctor, please repeat these two vectors.
Sorry, what?
Repeat this of two vectors.
So we have two vectors, two arbitrary vectors, right? V1 and V2. Any two vectors. And none of them is zero. V1 is non-zero, V2 is non-zero. We want to see when V1 and V2 are dependent, when V1 and V2 are independent, right? This is the question. So, we assume that V1 and V2 are dependent. And we check what this assumption gives us. V1 and V2 are dependent. So this system x1 V1 plus x2 V2 equals 0 has non-trivial solutions. In this non-trivial solution, at least one of x1 or x2 is non-zero. Suppose x1 is non-zero. So x1 is non-zero. So you can divide all elements in this system by x1 because x1 is non-zero. If you do so, you will get something like this. V1 equals minus x2 over x1 times V2. This means in this case, V1 becomes a multiplication of V2. This means if V1 and V2 both non-zero are dependent vectors, then one of them is a multiplication of the other. If V1 and V2 are independent, none of them is a multiplication of the other. Right?
Okay, Dr. Right.
Okay. Okay, let's move on. Okay. Now let's have a theorem. Let's have a set of vectors like V1, V2, 2VP. Let's have a set of P vectors. And assume that, none of them is zero. Because if one of them is zero, at least one vector is zero, this set will be dependent, we know. But we have a vector V1 and VP, and none of them is zero. This set is linearly dependent if and only if we can write at least one of these vectors in terms of a linear combination of its previous vectors. So at least we have a vector like Vj in the set, so that Vj equals a linear combination of V1 to Vj منهای Vj minus 1, C1, V1, etc. Plus Cj minus 1 V J minus 1, something like this. Right? Let's keep its proof, but you accept this. You accept this. So V1 to Vp are linearly dependent if and only if there exists at least one element like Vj, which can be written in terms of a linear combination of Vx to Vj minus 1. In other words, there exists at least one Vj, so that Vj equals C1 V1 plus C2 V2, etc. plus Cj minus 1 Vj minus 1, right? We see examples of this, but do you understand what this theorem says?
No.
Not exactly, doctor.
Okay, so let's move to an example. And we don't have example. Let me, what says this example? We will have examples in the in other slides. Let me find an example of this. Okay, so let me repeat it. Maybe you can understand, and then we see one. So, what this theorem says? So, we have a set of p vectors, right? V1 to Vp, V1, V2, Vp, right? And we want to see if they are dependent or not. They are dependent if we can write one of them in the form of a linear combination of its previous vectors. So they are dependent, V1 to Vp are dependent if, I mean, you don't try to understand what this theorem is correct, why this theorem is correct, right? You don't try to understand why this theorem is correct. Just try to understand what this theorem says, right? My point here is you understand what this theorem says. So this theorem says V1 to Vp are dependent if and only if we have one vector like Vj, which is equal to C1 V1 plus C2 V2, etc. Plus Cj minus 1, Vj minus 1. This means V1 to Vp are dependent if and only if we can write at least one of the elements in the set in the form of a linear combination of its preceding elements. Is it clear now what this theorem says? We don't want you to understand why. We just want you to understand what this theorem says.
Doctor, can you take example for this?
Unfortunately, here is very difficult to write on this. And if you were in the class, I could write very simply examples on the whiteboard. Okay, so let's assume we have two vectors. And we want to see if they are dependent or not. According to the previous according to the previous theorem, they are dependent. If we can write V in the term of a linear combination of its preceding elements, which is U. So these are dependent if V can be written as C, which is a number, times U. Right? So in other words, and equally, we can say these two are dependent if V is a multiplication of U. And in this case, V is not a multiplication of U, so these two are dependent. So these two are independent, because V cannot be written in the form of a linear combination of its previous elements, which is U. Is it clear? No. Let me see if I can find that's the thing. Over here, writing on this page is very difficult, and that's why I insist you come and attend the class in person. Let me Google. Huh? So,
Professor?
yes. You want to say something? I'm trying to find an example, because you were looking for an example, right? I'm trying to find an example because it's difficult for me to write on this page.
Yes, please, doctor.
Doctor, this video is stopped. We can't see.
And the question is whether they are dependent or independent. According to the theorem that I explained, they are dependent if and only if we can write one of them, for example, 9, 5, in terms of a linear combination of the others, the previous ones, like 2, 3, and 7, 2. Let's see if this is possible or not. Right? Okay. V3 as a linear combination of its preceding vectors, which are V1 and V2, and as a result, V1, V2, and V3 are dependent, right? Is it clear? Because we could write V3 as a linear combination of V1 and V2. Is it clear now? So V1, V2, V3 are dependent because we could write one of the vectors, which is V3, in terms of a linear combination of the previous vectors, which are V1 and V2. Because we see that V3 equals V1 plus V2. Is it clear to you now what that theorem says?
Yes, doctor, it's clear.
Okay, great. So that theorem says a set of vectors, I'm repeating it again. That theorem says a set of vectors are dependent if and only if we can write one of them, at least one of them, in the form of a linear combination of previous vectors. In this example, V1 is 2, 3, V2 is 5, 2, and V3 is 9, 5. We can write V3 as 1 times of V1 plus 1 times of V2. So we can write V3 as a linear combination of V1 and V2. This means these three vectors are dependent, right? Is it clear to everyone?
Yeah, doctor, clear.
Yes, doctor.
Okay, if
For me, it's clear.
Okay, let's continue our normal of U, because V is not a linear combination of U, right? V is not a linear combination of U, because V is not equal to CU, right? So these two are independent,
Yeah.
right? Do you agree?
Okay, doctor.
Right, doctor, right. We agree.
Okay. So now that these two are independent, consider a span of these two vectors, a span of U and V. What is the definition of a span? Do you remember?
Yeah.
Yes, doctor.
So let me know what is definition.
Of this span, doctor?
It's
What is
span is the shifting of the vector that U and plus X.
Exactly. This is the set of all linear combinations of U and V, right? A span of UV is the set of all linear combinations of U and V. A span of U and V is the set of all linear combinations of U and V. It contains each vector which can be written as the form of a linear combination of U and V, right? This is the definition of a span. So show or explain that a vector W is in the span of U and V if and only if U, V, W is dependent. Who can do this? Who can explain a vector W is in the span of U, V if and only if U, V, W is dependent?
Doctor, the vector W not at the origin, point origin, and the other in the point origin.
It's not origin. W is any arbitrary vector. It's not necessarily the origin.
Doctor, if we suppose that x3 is 0, it actually is x3 was equal to 0. The span of u and v is the x1 and x2 plan. So the w is the between u and v. U and v is linear independent. That's the proof of the theorem 7.
Yes. Yes. Continue, please. Yes.
Okay. So we suppose that that v is not a multiple of u. So that it's not independent.
Yeah.
Because the result of w it's different between them.
Okay, so it's almost correct. Let me explain it in a more clear way. So, if W is in the span of U and V, then we can write W in terms of a linear combination of U and V. As a result, U, V, W are dependent, right? Because one of the elements of this set, which is W, can be written in terms of a linear combination of previous elements, which are U and V. And according to the previous theorem, in this case, U, V, W is linearly dependent, right? So W, let me repeat it. W is in the span of U and V. According to the definition of span, W equals a linear combination of U and V, right? This is the definition of span, right? So when W equals a linear combination of U and V, according to the previous theorem, U, V, W, this set is linearly dependent, right? Is it clear? If it is not
Unfortunately,
clear,
no.
Sorry?
Not exactly, doctor. Not really.
If it is not clear, then you don't follow, you don't study the materials of the course, because this is exactly definition of span that we already discussed. W is in the span of U and V, right? Based on definition of span, what span means? When W is in the span of U and V.
Span mean variable multiplied by vector.
No, it's a part of the original vectors.
No, when W is in the span of U and V, then this means we can write W in terms of a linear combination of U and V. You forgot it, right? Let me bring the slides. Why did you forget? You didn't continue. Let me see. Okay. Let me open this file. But you don't study the material of the course, and I think that's the reason. that you don't. So, is this correct? That you don't study?
Yes,
Or
doctor,
not?
maybe.
Okay. So, let's back to this. So, if W is in the span of V1 to V1 and sorry, if W is in the span of U and V, then W equals C1 U plus C2 V. This means W can be written in the form of a linear combination of U and V. And according to the previous theorem, this means U V W is linearly independent. Yes, sorry, linearly dependent. All right.
Yes, doctor. Right.
So, did you understand this?
I understand this.
Okay, great. Okay. So, UVW will be dependent if and only if W is in the span of UV. And UVW will be independent if and only if W is not in the span of U and V. All right, okay. So let's move to the next theorem. The next theorem says that if we have some vectors V1 to Vp, we have P vectors V1 to Vp. And each vector is in Rn. Each vector has n entry. If the number of vectors P is greater than n, then these vectors will be always dependent. Let me repeat. So we have some vectors like V1, V2 to Vp. We have P vectors. And each of these vectors has n column, n entries. Each of these vectors is in Rn, right? And the number of vectors P is greater than n. In this case, these vectors will be dependent. Why? It explains. Because if we consider the system of these vectors, the همگن متجانس or heterogeneous system of these vectors, the coefficient matrix will be something like this, V1 to Vp, right? And since we cannot have two pivot positions in the same row, we will have at most n pivot positions. And since P is greater than n, at least some of columns will not have pivot positions. So they will not be pivot columns, and the variables will not be basic variable, and the variables will be free variables. And therefore, we will have free variable, and we will have many solutions, trivial and non-trivial. And vectors will be dependent. Is it clear to you?
No, doctor. Can you repeat, please?
Okay, let me repeat first what this theorem says. This theorem says if we have P vectors, and each of these vectors has n entries, then if P is greater than n, if the number of vectors P is greater than n, these vectors will be always dependent. Do you understand what the theorem says?
Doctor, please, n represent the entries of each vector, right?
So we have p vectors, and each vector has n entries, n cells, right?
But the number of vectors is greater than the entries of each vectors.
Exactly, and p is greater than n.
In this situation, we can say that it is linearly independent.
Yes, in this case, we can say that V1 to Vp are always linearly dependent.
Because we have more columns.
Yeah, we have more columns than rows.
Than rows, yes, than n. It's
Exactly.
more than n.
Exactly. That's the reason. Yeah, so continue, explain this to your friends.
Sorry, doctor.
اشرحي لنا.
اشرحي لنا ست نور بلا زحمة عليك شنو اللي قصده.
ها اوكي. يقول اذا احنا عندنا عدد البي اكبر من الان راح يكون دائما linear dependent. ليش؟ لانه احنا الان هي البي هي مجموعه الفيكتورز، والان هي الانتريز داخل الفيكتور، فاحنا من نجي يعني نسويهم بالكوفيشنت ماتريكس البي راح يصير اكثر من الان. ليش؟ لان البي مجموعه الفيكتورات هن الكولومز، والان هي الاسطر الرو اللي هي الانتريز مالتها. فبهاي الحاله دائما يكون عندنا اللينير ديبندنت. ليش؟ لان راح يكون عندنا فري فاريبل على يعني باغلب الاحيان، ومن يكون عندنا فري فاريبل فراح يصير عندنا مور ذان وان سوليوشن، فراح يكون عندنا لينير ديبندنت.
يعني بالحالة إذا كان عندنا free variable نقدر نقول عليها linear dependent، وإذا ما كان عندنا free variable
هو ممكن تكون linear dependent إذا عندنا free variable، بس إذا يدخل وياها الإسبان لا راح يعني راح يصير تشويش عندنا، لأن إحنا الإسبان راح يصير عندنا لازم الفكتورات كلهن نفس الإسبان، ما يعني مو المالتيبل مالتهن. بس
يعني
ست نوع
هنا ما راح يصير بها حلين، ما راح تصير متوازنه المصفوفه يعني مثلا 5 اعمده وثلاث صفوف ما راح متوازنه، ما تصير متوازنه.
بس دائما بيناتهم ديبندنت. هو ما له علاقه انه هي متوازنه او لا، هو له علاقه انه اكو فكتورات وبيهن انتريز، بيهن عناصر. زين هاي الفكتورات اذا اكثر من العناصر اللي بيهن فراح تكون ديبندنت، راح تكون يعني بيها اعتماديه بين فكتور على فكتور ثاني.
هي الديبندنت هي بها 4 شروط لازم يتحققن يلا يصير ديبندنت، من ضمنها الفري فيرابل.
اي لان هو احنا هنا اول تالي هم يعني هم راح يطلع عندنا فري فاريبل
اكيد.
اي.
So did you understand? Did you get the point now?
Yes, doctor.
Yes, doctor.
Okay, great. Okay, so if you get the point now, I think we are running out of time. We can stop here. The lady who answered this question, I will consider a class for you. Please let me know your name, and I consider a class for you. The lady who answered this question and then she explained this to the others, I will consider a score, a bonus for her. If she...
Okay, doctor, my name is Noor Farhan Abbas.
Farhan Abbas, right?
Yes, doctor.
Okay, Farhan Abbas. Okay, so if any of you answer questions in the class, I will consider plus for you. So this plus can help you to get a better grade in the final exam. So you can consider this. So if you are active and you actively participate in the discussions and you understand the material, answer my questions, and then you can even explain your answer to your friends, then you will get a bonus. Okay. So if you have any question, let me know. Otherwise, we finish here.
Okay, thank you, doctor.